Picking right up after repolarization, we'll now look at hyperpolarization. You can use a purple highlighter and go over that orange part. I don't know, maybe circle it. And that's number 5, purple. And we call that hyperpolarization. And the reason that happens is because potassium channels close slowly, allowing the cell to be momentarily more negative than at rest. Alright, so now though you're at the situation where how do you get back up to where you started? And this is where that pump is so important. Right here, I'm going to use a black pen. The sodium, potassium, remember it's 3 sodium, 2 potassium, ATPase pump, busily returns sodium to where it started, which is outside of the cell, and returns potassium to the inside of the cell. So it's important for bringing it back up to rest, and then the pump maintains that resting membrane potential until the next action potential is fired. Any kind of a poison or an illness that affects this sodium potassium ATPase pump, or a venom from a snake, will kill you if not reverse promptly, because without the sodium potassium ATPase pump you could not keep firing action potentials, because eventually you would lose the negativity that the cell has. Okay, now we'll look at this action potential and just put a few more things on there. So with a pink pen, you could mark right here that this is threshold, and at that point, then with your green pen, at that point, all the sodium channels open. And it seems like almost just as quickly you go up, whoosh, all the way to the top, and then at this point, all sodium channels close. And then potassium channels open. So you start to see this pattern, right? If sodium channels are open, then the cell it depolarizes. If potassium channels are open, the cell repolarizes and even hyperpolarizes for a little bit there. Remember I mentioned that the frequency of the action potentials is how intensity is coded. I'm going to write that again for here. And let's look at this. If one line represents an action potential, then tell me about the intensity of these 2 lines. You can see pretty easily, right, that this is not very intense and this is intense. I like to think of it as ringing a doorbell. In my neighborhood, we have lots of little 2nd grade boys. I have a 1st grade little boy, and they love to play together. Well, they don't like to wait for a door to be answered, right? So if you go up to a door and you ring the doorbell, on the inside of the house you hear ding dong, or whatever yours does, right? Well, what happens if the child really wants you to answer the door? Does the inside of the house go ding dong? No, right? It can't go any louder. So instead it just goes ding dong, ding dong, ding dong, ding dong, ding dong until you're about ready to like scream at the kid, right? And give them a little lesson in etiquette on doorbells. So this is what goes on in my neighborhood. Well, that's what I mean by increasing the frequency of the action potential. The doorbell or the action potential doesn't get any louder. It doesn't go any higher than plus 30. And yet the body is able to interpret the frequency of the action potentials as great intensity of either sensation, right? If it's like how hard someone's touched you, or how much you want that muscle to contract and how strongly you want it to contract. So whether it's sensory or motor, increasing the frequency of action potentials is all that's needed to code for intensity. Okay, now to show you though, you can only increase the frequency at certain, like you couldn't have it any closer together than right here, let's say, right? I mean, this has to finish. Let's see, I'm not saying this very well. Look over here. If you have an action potential go up, it's got to come back down before it can go up again, right? Like this would probably be as fast as you could get them going together. So there is something called the absolute refractory period when it doesn't matter how intense the signal wants to be. You can't fire two action potentials at the same time. So there's a limit to that. And then there's something called the relative refractory period where if the stimulus is strong enough, you could fire another action potential. But you can only have the action potentials so close together. Think about this with the doorbell. It might depend on what kind of doorbell you have, but in my house, if the kid is pushing the doorbell, pushing the button too many times, instead of hearing a ding dong, I start to hear a ding 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 like that, and it goes a little bit faster, but it's not getting the entirety of the ding dong. So it can only go so fast. Or if the kid's pushing it, let's say the kid is pushing the bell 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On the inside of the house, you might still only hear ding dong, ding dong, ding dong. You might only hear it 3 times. So there's a limit to how quickly the action potentials can come together. Okay, there's one more thing I want to have you put on this page, and that's to get a big picture idea of where all this is happening. Okay, so these are dendrites. Here's an axon hillock, and then some nodes of rhombier. Now use a different pen. How about pink? That'll be perfect. This is where graded potentials occur. It's where we've colored pink. Are in dendrites. And they might look like this. A little blip that way. So either up or down. So either a blip up or a blip down. But notice that they never got to the height of an action potential. And then that kind of diffuses to the axon hillock. And why don't we just use green there. If threshold reached, AP is fired. But it also goes back to normal. And then at each one of these, you get propagation again. It has to happen all over again. And that is propagation. You could write, maybe you can write that sideways. Propagation. And instead of fired, maybe generated. You could write up